In this example, we're going to prove that polynomials are continuous on their domain. And when we do this, we're going to be writing the abstract form of a polynomial. It's going to be a long sum of coefficients times powers of x. And it's just a fancy way of showing a general polynomial. So let's get started here. Proof. We're going to use limit laws for a, an element of the domain of the polynomial p of x. So we're going to be taking the limit as x approaches a value in the domain of the polynomial. The limit as x approaches a of p of x is equal to the limit as x approaches a of this strange way of writing a polynomial. The constant c sub n times x to the n power plus the next coefficient c sub n minus 1 times x to the n minus 1 power plus dot 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 c sub 1 times x plus c sub 0. Now what we know, we can distribute the limit across addition. So we are going to apply the limit to each of the terms in the polynomial. And on the next line, we're going to pull the constants, the coefficients c sub n minus 1, etc., out in front of each of these terms, the limits of each of these terms. These are all things that we can do using the limit laws. And now we're ready to evaluate the limit of x to the n power. Well, the power law for limits says that we can just do a direct substitution. That's a to the n, and then the limit of x to the n minus 1 is a to the n minus 1 dot dot dot. The limit of x to the first is just a to the first, and then the constant at the end. Well, that's the same as a polynomial evaluated at x equals a, and therefore we've shown that we have continuity for the polynomial. Remember, what it takes to show that a function is continuous means to show that the limit as x approaches that number of the polynomial is the same as the y partner of x equals that a in the function.